you have ever made something, you must have heard the saying, measure twice, cut once. What's meant by this? Well, it's meant that you should check measurements before you cut anything, before you make anything permanent. But what happens if your two measurements are very different? Which is correct? How would you know? Really, it should be measure thrice and cut once, so you can check which measurement is correct and remove the error. In this video, I want to talk about errors or uncertainties in measurements. So to do this, I will discuss what is meant by error, uncertainty, accuracy, precision and resolution, how errors in measurements occur, how we calculate uncertainty from a series of measurements, how we combine uncertainties in calculations and quote them in our answers, and what do these errors mean to our answers? Does it mean that our experiments are no longer valid? Throughout this video, I will use the terms error and uncertainty, and in our courses they're almost interchangeable. However, they do have proper definitions. Error is how far from the correct value our measurements are, and uncertainty is our way of quantifying the range the true value may be in compared to our measurement. From here, three more terms that help are accuracy, precision and resolution. In everyday language, most people can use these words interchangeably. However, in science we have clear definitions of each. Accuracy, this is how close the correct value is to our measurements. Precision, this is how close our repeated measurements are to each other. Resolution is the smallest increment a device can measure. The easiest way I think of to remember these is to link them to an archer. Precise archers land their arrows close together. Accurate archers, on average, land their arrows close to the target. Now a high resolution target would have thin lines between the areas and many areas across a target, meaning it is easier to decide which value each arrow scores. An accurate, precise archer shooting a target with high resolution would put all their arrows in the same part of the target, hitting a very fine spot, scoring the maximum points. How errors occur in measurements. There are three sources of errors we encounter in experiments. The first type we encounter is called the blunder. This is caused by the experimenter making a mistake in their measurement somehow, such as putting a ruler in the wrong place or bumping into something. These we cannot take account for, and we just got to simply redo those measurements. The next two types of errors will be inbuilt into an investigation, and we have to take them into account in our uncertainties quoted in our final answer. The first of these is a systematic or a zero error. These normally occur due to a fault in the measuring device, and they will affect the accuracy of the measurement but not the precision. They can occur because the device has been improperly calibrated. For example, a digital balance that has been incorrectly zeroed, or a caliper that maybe has a bent jaw. Now, removing these errors from data is easy. If we take our balance for example, we know what the reading is with nothing on it, we simply subtract this from all our measurements. Spotting systematic errors can be hard, because all our measurements will be out by the same amount, and we do not know what the true value of the measurement should be. So how do we take account for this error? Graphs are probably the best way to spot a systematic error. Systematic errors will cause a line of best fit to be too high or too low, changing the intercepts. They shouldn't affect the gradient though. This is why they're called zero errors, because they affect, if we're expecting a graph to go through 0, 0, they affect where that goes through. The third type of error are random errors, and these cause our measurements to fluctuate either side of the true or correct value, meaning that if we take enough results, they will average themselves out, and should not affect the accuracy of our results, only the precision. This is why if we have random errors in a measurement, we take sufficient repeats to average out those errors. The fact they have little or they should average each other out means they shouldn't have any effect on a graph, or it's difficult to say what effect they'd have on a graph. Unlike systematic errors, random errors can be far easier to spot because they're causing the variation in our readings. Identifying the source of these errors is not always possible. However, some common sources are. Parallax error. Some people would say this is a systematic error. Personally, I think this is a random error because you might not be reading exactly from the same point each time. But parallax error occurs when you do not read a scale from directly in line, the pointer on that scale. Meaning you see the number slightly differently depending on whether you're reading too high or too low. This is why if you look at many high-end analog devices, you will see a thin mirror behind the scale. This makes sure you're lined up in the right place. Another source is reaction times. So if you're having to time something, you're having to start and stop that stopwatch precisely. Your reaction times mean that sometimes you'll stop it too soon and sometimes you'll stop it too late, making your times shorter or longer than they should be. You might also come across other variables that cannot be readily controlled. For example, if you're doing an experiment involving living things, there may be other things that are affecting their behaviour that you can't control. Once we've identified these errors, we can estimate the uncertainty caused by them. Calculating the uncertainty in a measurement. Now this next bit depends on your course and your exam board, because each one does things slightly differently. Heck, even WJEC does different things between chemistry and physics. So I'm going to talk about how WJEC Physics handles errors, as the more general way that other exam boards handle errors, available in other places such as YouTube, and I'll put a link in the description below to some videos on that. In the lab book then, the WJEC state that it is reasonable to expect the uncertainty in a measurement should be no more than the resolution of the instrument. This is where they differ to most others, but for us it simplifies the treatment of errors and uncertainty, so we'll run with it. So I want to find the length of this piece of paper. I'm going to use a ruler. Sensible thing to do. Now, when we make this measurement, we have to judge where the 0 point lines up. The paper might be a little bit one way or the other, and this introduces an error to our measurement. And we'll have to do the same thing at the other end of the piece of paper as well. Now, we can only line these up to the nearest millimetre because that's what our ruler measures to. So we get plus or minus a millimetre at this end, plus or minus a millimetre at the other end. So we've got plus or minus 2 millimetres overall. So in this case, our ruler is going to be, our paper is going to be 14.8 plus or minus 0.2 centimetres. Now in that measurement you can see that I've included both my reading, the 14.8, and my uncertainty, 0.2, and then I put my units on the end. Now for most scale readings, scale where we've got an analog scale like this, we're going to be plus or minus the resolution of the scale. Unless you are reading from one point to another, then you're going to be plus or minus 2 times the resolution of the scale. So a ruler, plus or minus 2 millimeters. A micrometer, which I don't actually have to hand, but a micrometer, so let's have a picture of one, will be plus or minus 0.01 millimeters, because there's no zero measurement on these. So what about a digital scale? These remove all human judgment. You're not judging, does something line up with this on this? But they still have errors in them. Or digital scales have to truncate or round a measurement to the digits they can display. This is why sometimes you might have seen scales hovering between two certain numbers, because it's on that error between the two. So any digital scale has an uncertainty of plus or minus their resolution. So in the case of these calipers, it's 0.01 millimeters. So if I was to measure my piece of paper again, which is tricky with the calipers like to squish things. So measuring a piece of paper is a little bit tricky. As you can see, I can squish it in. But if I measure my piece of paper, I get 148.16 millimeters. Plus or minus 0.01 millimeters. Now this measurement and this measurement agree. Within the resolution of the ruler, within the resolution of this, these agree. More on that later. Uncertainty in a series of results. Now, remember, we take repeat readings to average out random errors. But how do we express the uncertainty in this measurement? We cannot simply go with the resolution of the meter, because we may not know what it is, and we can clearly see that there is greater error than this, greater uncertainty than just the measurements there. So we use the range. Uncertainty in repeated results is half the range of the repeats. Because remember, we should be doing enough repeats to average each other out. So there should be some as high and as low from the middle. However, if we find that half the range is less than the resolution of the device taking the measurement, then we use the resolution of our uncertainty. Okay, combining uncertainties. So many times we have to combine results to calculate a required value. For example, if I want to calculate the volume of this block, we need to use the values of the different dimensions and combine them and their uncertainties to get the volume. And that will give us a possible range for what the true volume of this block lies. Now, we've already touched on combining uncertainties when we discussed uncertainty in a ruler. Where measurements are added or subtracted, like in our ruler, we add their uncertainties together. Hence why we said ruler measurements are plus or minus 2 millimeters. The 1 millimeter from each measurement we've taken, the 0 point and the end of the block. Now, if we multiply or divide measurements, it's a little trickier. Here, we add the percentage uncertainty in each measurement. To calculate the percentage uncertainty, we do percentage uncertainty equals uncertainty divided by the measured value. Uncertainty here is the resolution of the instrument, or half the range, depending on how it's being measured. Okay, so back to the block. What I'm going to do is measure the volume twice. Once using a ruler, and second, using a caliper, comparing the values and the uncertainty we get. Now, before we start though, people could ask, got a tape measure here, what about a tape measure? Now, have you ever noticed with a tape measure that they have a wobbly bit on the end, even when they're brand new? And now this is to do with uncertainties. Because tape measures we can use to take two types of measurement. They can be either used to measure an interior measurement, like so measuring the distance from the desk up, or an exterior measurement, where we stretch this end piece over an object. And if you think about it, that means that this end piece is either in the measurement when it's down or excluded from the measurement when it's stretched. And this is why they wobble, because that wobble is roughly equal to the width of the piece of metal on the end. There we are. Anyway, that was an aside. Let's get back to our block. So here's our block. So let's take our measurements then. We will need a pen. Let's grab the pen. Here's a pen. Okay, so we'll start with the ruler. So our ruler, our block is going to be, we'll work in millimeters on both. So this is going to be 96 millimeters. So I have 96 millimeters. That was that one. Now we'll measure this one. And this one is 94 millimeters. And then our final measurement is this measurement, and that is 45 millimeters. So that's with our ruler. And remember, they're all going to be plus or minus 2 millimeters. Now what about a caliper then? So the caliper, we switch it on, we make sure it's 0 before we start. Caliper like so, and this is then 44.8. This measurement is 94.11. 44.8. 44.83. 94.11. And then our final measurement is 96.66 millimeters. Now, one thing you'll notice talking about systematic error is that sometimes, especially digital calipers, they don't always quite go back to the same point on 0. So you can get systematic errors built in with your caliper. So, and our caliper measurements will all be plus or minus 0.1 millimeters. Now, from these measurements, we then go on to work out the volume. So the volume is going to be the 3 measurements multiplied by each other. Okay, so we've measured our block and we've come back outside, so we have our lovely wall to put our measurements down on there again. So remember, with our ruler, it was 96 millimeters plus or minus 2 millimeters. Now, if we work out the percentage uncertainty of this, we do 2 divided by 96 to give us 2.1%. For the 94 millimeter direction, again, 2 divided by 94 gives us about 2.1%. 45 millimeters, 2 divided by 45 gives us 4.4%. Now, remember, going back to our standard form and significant figures video, there is no point me giving any of this data to more significant figures than I've started with. So I had 96, no point me giving it to any more than 2. Okay, if we work out the volume to begin with, again, we want a volume to 2 significant figures. So if we put these numbers into our calculator, got them written here, it's 406,080 millimeters cubed. We don't need all those digits, we only want 2 significant figures. So it's going to be 410,000 millimeters cubed. So what about our uncertainties? Well, we said if we have multiplication or division, then we add their percentage uncertainties. So in this case, we add our 2.1, our 2.1 and our 4.4, and we get 8.6. So we could say that our volume of our cube is 410,000 millimeters cubed plus or minus 8.6%. Now remember, we probably only give out to one significant figure, one less, so 9%. Now that's great, but what does 9% mean? Let's actually have a number range. So what we do is we go back, we take that number, we take that percentage. So we find 9% of our original value, and that gives us then, it's 410,000 plus or minus 30,000 millimeters cubed. Alright, what about our caliper then? So our caliper measurements, remember, were 96.66, 94.11 and 44.83. We work out our percentage errors here and we get 0.01, 0.011 and 0.022% respectively. This gives us an overall percentage error with our caliper of 0.043%. We work out the volume using our caliper and what we get here is 407,804 millimeters cubed, or again, we are now working to 4 significant figures, so that would be 407,800. Okay, combine our percentage uncertainties, we get an overall percentage uncertainty of 0.043%, which works out as plus or minus 180 millimeters cubed. So for in our caliper, we would say that it's 407,800 plus or minus 180 millimeters cubed. Now you can see that our caliper range is a lot smaller than our ruler range. But if we look at our ruler range, our caliper measurement lies within that. So the two measurements do actually concur. Although the values are ever so slightly different, because the two overlap, they do concur, and we'll go into this in more detail. So what about formulas that have powers in them? Well, we just multiply the percentage uncertainty by the power, because remember, powers are just like multiplying by that number multiple times. So if we have squared, that's 2 times the percentage uncertainty. If we have a square root or other roots, these get a bit trickier, but that's where we would half the uncertainty. Because remember, a square root is the same as raising something to the power of a half. Now the final thing when it comes to uncertainty is, what about if we use a part or a fraction of our measurement? So for example, if we time a pendulum, to reduce the effect of our reaction times on the time period, we're going to time 10 swings. And then we will take 1/10 of this time to be the time of 1 swing. So what happens to our uncertainty? Well, we will take it to be 1/10 of the original uncertainty. Although we do take care with resolution here, because remember, reasonably we can only time to about 0.1 seconds. A little piece to add on the end, we can also use graphs to calculate uncertainties, but I've left that for another video where I talk about graphs in detail. Now, just quickly back to the block. Remember I said that our two volumes with their range of uncertainties meant that both experiments were valid, because the volume of one was within the range of the volume of the other. Now, uncertainty, back to its definition, gives the range in which the real value lies, and this is important because one of the classic experiments that we do is we use free fall to calculate a value for the acceleration due to gravity. Now at A level, we tend to take this number to be 9.81 meters per second squared. But if we do the experiment, we might calculate it to say be 10.5 plus or minus 1 meter per second squared. Now does this mean our measurement is wrong because we didn't get the 9.8 we set out to find? Well, no. Because if you think about our answer, 10.5 plus or minus 1 meters per second squared, what are we saying here? Well, we are saying that our measurement lies somewhere between 9.5 and 11.5. Now, if we take a look at this diagram, show you that on the number line. So, as our real value, 9.81, lies somewhere in this range, our investigation was correct. It does back up our original thoughts. Okay, on to some examples. Now you'll be glad to know there is no Isaac physics assignment to practice errors and uncertainties. At least for physics, for WJEC Physics, because they treat errors in a different way. They treat them in the more general way the WJEC Physics does not. So instead, here are some examples for you to try. In a minute, pause the video and attempt them, as I'll go through the answers afterwards. Okay, so number one, the current I is measured 4 times with these results. Give the reported value of current together with its uncertainty. Question 2. The potential difference, V, across the component is 5.35 plus or minus 0.2 volts. The current is 25.3 plus or minus 0.8 milliamps. Calculate the value of resistance of the component together with its absolute uncertainty. Now, take care there, you've got milliamps. You're going to need to use amps in your proper equation, but you can use your milliamp answer when you're working out the percentage uncertainty when combining them. Because what you will do is you will divide both the measured value and the uncertainty by 1,000, divide both by 1,000, put them in amps, so it doesn't actually matter whether you use milliamps or amps when you're doing just the uncertainty bit. Question 3. The diameter of a sphere is measured as 2.00 millimeters. Calculate its volume, V, given your uncertainty. Now, if you remember back to our standard form significant figures video, we said something about trailing zeros and what they might imply. So I'm not actually giving you any other source of what the errors might be in that question there. Then question 4 is fill in the missing parts of the table. Alright, so you've got 4 columns to fill out. The mean time for 5 oscillations, your uncertainty in 5 oscillations, your mean time for 1 oscillation, and the uncertainty in 1 oscillation. Okay, the answers then. So if you've not done these yet, don't play on from here. So the first question, this is using a series of measurements. So you were to add them up, divide by 4. There are no clear outliers here, so we need to use all 4. Divide by 4 to get your mean, and then remember half the range will be the uncertainty. So the answer is 36.88 plus or minus 0.3 milliamps. Okay, question 2. So here we have to use Ohm's law to find the resistance, R being V divided by I. Remember where I needed to be in amps. So you get a resistance of 211 ohms. Now what about the uncertainty? Well, this is where we take the percentage uncertainty. So you find the percentage in the voltage, you find the percentage in the current, you add them together, and then you take that percentage of the 211 to give you the uncertainty. So your answer here should have been 211 plus or minus 7 ohms. Right, for question 3. So in that measurement it was 2.00 meters. So, sorry, not meters, millimeters. So our resolution here is 0.01 millimeters. Remember, trailing zeros imply resolution. So we work out our volume first. Volume of a sphere is 4/3 pi r cubed, to give you a value of 3.35 times 10 to the minus 8 meters cubed. Yeah, I've worked in meters cubed. So 3.35 times 10 to the minus 8 meters cubed. Then what we do is we find our percentage uncertainty. So that's going to be 0.01 divided by 2 times 100. Then we multiply that by 3 because we've cubed the radius. We multiply that by 3 and that gives us a value of 0.05 meters cubed. So our final answer here when we put that back into meters cubed to convert to meters cubed, it's all going to be in the same thing. So it's 3.35 plus or minus 0.05 times 10 to the minus 8 meters cubed. Perhaps you've given that in millimeters, and so in millimeters cubed, it's going to be 33.5 plus or minus 0.05 millimeters cubed. Then finally, the missing parts of the table then. So you do your mean time, so you add each row up, then divide by 3 for each row. So you get your mean times. Your uncertainty is going to be half the range in each case. Your mean time for the oscillation is going to be your mean time for 5 oscillations divided by 5. And your uncertainties are also going to be that divided by 5. Now take care, you should always record to the same number of significant figures throughout your table, as I've done here. Summary. To sum up, errors and uncertainties. Errors are things that make measured values end up different to the true value. Uncertainties are our way of quantifying how different our values are to the true value. Accuracy is how close we are to the true value. Precision is how close our repeats are to each other. And resolution is the smallest measurement a device can measure. The uncertainty in a single measurement is plus or minus the resolution of the device. The uncertainty in a series of repeats is half the range, unless this is smaller than the resolution. When we combine uncertainties, if we are combining measurements, if we add or subtract the measurements, we add the uncertainties. Always add the uncertainties. Doing anything with our data will make our uncertainties greater. If we multiply or divide, then we add the percentage uncertainty. An experiment will be valid if it returns a result where the real value lies within the range of our uncertainties. Now, if people want to see me actually doing the maths, the proper answers to those calculations, post in the comments below, and I'm quite happy to do a follow-up video where I go through those answers in more detail and I show my workings out. But otherwise, guys, thanks for watching. Like I said, there'll be links in the bits below to the other way of doing uncertainties. I probably will put the Isaac Physics in there anyway, but remember, if you're getting answers wrong doing it WJEC way, it's because they do it the more general way as per the videos that I put in the links. Thanks for watching. The usual things, like, subscribe, all that sort of stuff. Give us comments about what other videos you'd like to see in this series.